Hello folks, I'm Mr. Pinola, and today we're going to take a look at a little bit of a more in-depth approach to Newton's second law of motion. Now, we already covered Newton's first law of motion, otherwise known as the law of inertia. But as you might recall from the last video, Newton's second law also has two parts to it. And those parts are the parts that I've written up on the board behind me. The first part of the second law states that as your mass decreases, your acceleration increases. That's assuming that force stays the same. So if you were to have two objects that had different amounts of mass and they both experienced the same force, the less massive object would accelerate at a faster rate. In other words, the object with less mass would pick up speed or change its speed more quickly than the other object. This is sort of like how we talked about if you were to put the same car engine inside a small vehicle and inside a big truck. The small vehicle would accelerate or change its speed much faster than the truck would be able to. Both vehicles would eventually get up to the same speed, perhaps, but it would take the smaller vehicle much less time because it would have a faster acceleration due to its lower mass and both vehicles having the same engine. The second part of Newton's second law states that as the net force, and notice I'm saying net force here, that is more correct than just saying force. And we already learned a bit about net force. But as the net force increases, then the acceleration increases. A good example of this would be if you took two cars that were identical, they had the same exact mass, and you put a really powerful engine in one of the cars, and you put a not very powerful engine in the other car. The car with the engine that could deliver more force, so the more powerful of the two engines, would cause that car to change its speed faster, and so it would have a bigger acceleration. So, if your mass is the same, then a bigger net force will cause a bigger acceleration. So what you're seeing is that in order to generate a really large acceleration, you should have a couple things. You should have a really low mass and a really big net force acting on you. Imagine a very small car that didn't have much mass and a very powerful and strong engine inside that small car. That car would be able to change its speed super fast. It would have a huge acceleration due to the combination of a small mass and a very large net force. And so today we're going to take a look at an equation that can relate these two things. And so that equation says that the acceleration of an object will depend upon these two factors, mass and net force. But the equation is going to look like a fraction. And in that fraction, we will have net force, which I will abbreviate as F net, on the top of the fraction, and M for mass on the bottom of the fraction. The reason being, if we have net force on the top of the fraction, then it holds true that as the net force gets bigger, the acceleration gets bigger. Because as the top of any fraction gets bigger, the number gets bigger. And on the bottom, as the mass gets lower, the acceleration goes up. So it would make sense again that in the bottom or the denominator of our fraction, if this number gets bigger, then the acceleration or the result actually gets smaller because you're dividing by a larger number. Keep in mind that if you see a fraction as a mathematical equation, it really just means divided by. So in this case, you can calculate the acceleration of an object by taking the net force that that object experiences and dividing it by the mass of the object. Let's take a look in a second about how to use this equation along with our three-step method. Before we get into the heavy-duty mathematics, let's consider a specific visual example. Here on your screen, you see two examples side by side of different objects that are going to accelerate. In other words, these objects are going to start speeding up, and that's because they are both experiencing an unbalanced force. On the left side of your screen, we have a person that is pushing a refrigerator across the ground. The person is applying a force of 250 newtons, and since there's no friction, let's consider that 250 newtons the net force. The refrigerator also has a mass of 200 kilograms. On the right side, the person is not pushing a refrigerator anymore. Instead, they're pushing a man. And the man clearly has a lower mass than the refrigerator. So you might think, oh, the man on the right side is going to accelerate or change his speed quicker because he has a lower mass. But notice also that the net force being applied is lower on the man than it was in the refrigerator. So some folks might think that the refrigerator will have a bigger acceleration because there's a bigger net force acting on it. Whereas other folks might say that the man will have a bigger acceleration, and that's because he has a lower mass. So which is it? Which one is going to increase its speed at a quicker rate and therefore have a bigger acceleration? Well, we can do two things to find that out. We can hit play and watch the simulation, or we can use our calculations to come up with actual numbers and then go back and test. And like any good scientist, let's do the calculations first and get some actual numerical quantitative data and then see what the simulations show us. So let's go back to the board and use the three-step method first. Welcome back to our whiteboard as we will work on the three-step method to find the acceleration for the refrigerator and the man. I'm going to do the work for the refrigerator first in blue marker. So I will write refrigerator. And I'll show you the calculations that come along with this. So whenever we do the three-step method, and I'll divide my paper into 3 columns, we first write out our given information, the stuff that we know about the problem. So let's do our givens first. In the refrigerator example, we know that the mass of the refrigerator is 200 kilograms. It's a really big object. Notice that we're using kilograms for mass. Kilograms is the SI unit for mass. We also know that the refrigerator experienced a net force of 250 newtons. Remember, newtons, the SI unit for any push or pull, which is a force. Lastly, we want to see how quickly the refrigerator is picking up speed. So we don't just want to find speed. We want to find its acceleration. Because we want to find how quickly it changes its speed. So I'm looking for acceleration. And I'm also going to note that acceleration is measured in meters per second squared. So let's now go to our calculation. We're going to use the equation that I showed you earlier. A equals F net divided by M. And I don't need to reorganize this at all. It's already solved for A. So all I have to do is plug in some numbers. I will do that. A is equal to the net force of 250 newtons divided by the mass of 200 kilograms. Doing my math out, 250 divided by 200. I'm going to plug that into my calculator. And I get an answer of 1.25. But don't forget units for your value. Remember, the units for acceleration are meters per second squared. And so we will also include that. This tells us that our refrigerator is going to change its speed by 1.25 meters per second every second. Let's compare that now to the man and see if he picks up speed at a quicker or slower rate. So now let's do our calculations for the man. I will do this work in brown. We're going to collect our given information first, just like we did before. And so our given information tells us that the man's mass was only 80 kilograms. He had a lower mass, which is why many of you might be suspecting that he's going to have a faster acceleration. Let's see, though, because the man also experiences a lower net force of only 150 newtons. This is why we have to do the math out. It's not super clear. The man has a lower mass, which would mean he would accelerate faster, but also a lower net force, which means he might accelerate slower. So we should do the calculations out to get numbers. Once again, we're solving for his acceleration in meters per second squared. And then I'm going to go to step 2. And even though I didn't label it before, step 2 is where we always write our equation. And we reorganize the equation if we need to. In this case, we're still going to use the same equation to find acceleration. And there's no need to reorganize it because A is already by itself. Then we'll come to our last step. And again, I didn't label it before, but our last step is where we do the math and we plug into the equation we had in step 2. And so I'm going to write that A is equal to F net, which is 150 newtons, divided by the mass, which is 80 kilograms. And if I do my math out, 150 divided by 80 is equal to 1.875 meters per second squared. According to our data, the man picks up speed more quickly than the refrigerator. Let's go back to our simulation and see if that is indeed true. Welcome back. We found from our mathematical work that the man is going to pick up speed faster than the refrigerator because the man had a higher value for his acceleration. Let's put them both in motion, and I'd like you to watch their speed and see which object is picking up speed more quickly. Here we go. We'll start them at roughly the same time. It's starting to become pretty clear if you look back and forth. The man's speed is increasing at a faster rate. He has a bigger acceleration. But sometimes the three-step method with the equation for Newton's second law is not as easy as I just showed you. So let's consider another example. Let's say that we are told that the mass of an object is 30 kilograms. And that the object has an acceleration of 1.5 meters per second squared. In other words, the object is going to increase its speed by 1.5 meters per second each second. Well, this time we're asked to find what is the net force that acts on the object. And these are our givens in step 1. Well, now when we come to step 2, which was where we write in our equation of the three-step method, it gets a little bit more difficult because our equation says that A equals F net divided by M. Aren't we looking for net force, which should be measured in newtons? F net is not by itself. we need to get it by itself. And so we have to do a little bit of work with the letters here in step 2 before we move on to the math. Do you remember how to get rid of a fraction in a mathematical equation? A lot of people think you should multiply by whatever's on top. You should not. Instead, to get rid of a mathematical fraction, in this case, to get f net by itself, we should multiply by whatever is in the denominator, whatever is in the denominator or the bottom of the fraction. So I'm going to multiply by m, not by f net, so that the m's cancel out. And then I will multiply the left side by m as well. This leaves me with m times a equals f net. And that is the equation that we're going to use now to find f net. In fact, sometimes people will jump right to this step and write the equation in this form. Totally acceptable too, but I would just know how to go from this original equation, multiply by m on both sides, and set up this new expression here. So, to finish out our work, we're going to do a bit of math. And so we will say that f net is equal to the mass, which is 30 kilograms, multiplied or times the acceleration of 1.5 meters per second squared. And if I take out my calculator and I do 30 times 1.5, I get a net force, F net, of 45 newtons. And that means that to give a 30 kilogram object an acceleration of 1.5 meters per second squared, I need to use a net force of 45 newtons. Let's do one last three-step mathematical example. Let's say now that you are told that an object of unknown mass, so now we're trying to find the mass in kilograms, experiences a net force of 70 newtons. And the object, as a result, gets an acceleration of 5 meters per second squared. A really fast acceleration. This object is increasing its speed by 5 meters per second for every second that it's in motion. It's getting really fast, really quickly. So let's go to our equation. We're going to go to the same one we did before. A equals F net divided by m. This is the mathematical expression of Newton's second law. And we might notice that m is not by itself. So the first thing we need to do is get rid of the fraction. Remember, we get rid of the fraction by multiplying what's on the bottom. Don't be tempted to multiply by F net. Don't multiply by what's on top. Multiply by what's on the bottom. The m's cancel out, and we now have m times a equals F net. But guess what? M is still not by itself. We have to do a second step here. In order to get m by itself, we need to now divide the left side by a, so that the a's cancel on the left. And we have to divide the right side by a as well, meaning that m is equal to F net divided by a. This is the equation that we should use. So let's do that. We're going to come over to our math. M is equal to F net, which is 70 newtons. And A is equal to 5 meters per second squared. So I will take out my calculator and I'll do 70 divided by 5. And I will find that the mass of the object is 14 kilograms. If an object experiences 70 newtons as a net force and accelerates at 5 meters per second squared, its mass must have been 14 kilograms. I hope you learned something today about Newton's second law of motion. Last time we viewed a video together, we talked about how the second law of motion got developed, showing you that objects that have big masses take a very long time to change their speed, and objects that have very big forces take a very short time to change their speed. They have big accelerations. Today we put some math behind it, using the equation that A is equal to F net divided by M. I would know that equation, so make sure that at the close of this video, you remember that A is equal to F net divided by M. Because we are going to continue to practice with our three-step method, and on tests and quizzes, you will be expected to show your work using the same format that I showed you on the board in this video. Thanks for watching.